All right, good morning, everyone. The first research presentation of the day is led by Dr. PingYi, Professor of Civil Engineering at the University of Akron. Dr. Yi's research is mainly focused on traffic control and safety, sensor and information technologies, and system reliability and statistical data modeling. Prior to joining University of Akron, Ping had worked for the Minnesota DOT as a project manager over sensors testing, adaptive signals, advanced parking, and incident special event management. In recent years, Ping has been actively involved in research concerning safe operation of autonomous vehicles and their interaction in built environment with conventional vehicles. This presentation is titled Impact Analysis of Roadway Surface and Vehicle Conditions on Fleet Formation for Connected and Automated Vehicles. Rolling resistance largely affects the safety of emergency braking, and it changes with road conditions and other environmental factors. This presentation discusses a condition-dependent, time-resolved approach for estimating disturbances from variations in the roadway environment to the operation and fleet keeping of CAVs. The research work focuses on the internal dynamics of acceleration and vehicular interactions when such external factors are exerted on the CAV fleet. The implication to the safe operation and critical inter-vehicle spacing is discussed. So without any further ado, Dr. PingYi.
Thank you, Kelvin, and welcome. Still good morning. My presentation is about fleet formation of connected and automated vehicles in the realistic environment, driving environment. We have seen so many published, papers and reports in recent years, especially those that deal with operations, that a vehicle fleet in the context of autonomous vehicles always assume to have similar features in terms of the vehicle size, weight, engine power, ability to brake, and tire condition, everything. That's why in the published work you see, pretty much the fleet is like closely spaced, sort of like in a uniform spacing. We know that in reality, this is very difficult to do, right? Because we may be able to, group up some vehicles that are going to the same destination, in other words, with the same OD. But then it's very difficult, I assume, to really require them to be similar, in all those features. So in reality, what we should do, mainly two focus issues that I want to discuss today. One is regarding the roadway resistance. Many people have an impression that roadway resistance is the main factor, is the most important, or sometimes is the only factor that affects the vehicle's ability to stop. Now we're going to discuss this. In reality, we'll show that it's not the case. In addition to that, we have to consider vehicle condition. Okay, we will have to also consider the tire condition and the environmental condition, for example, rain and snow and ice. So that's one issue we're going to discuss. And the other one is we want to build a model. It's more practical. Okay, we want to build first a base model, and then we'll consider the effect of those conditions, those different factors on the vehicle formation. This. All right, let me just quickly go through some background with regard to the safety. And this is 1918 data, because 1919, 20, and 21, we know that is, because of COVID and not realistically reflecting the situation. But in 1918, you can see that, 37,000, deaths. And that also involved 52,000 vehicles. So that's a huge number, okay, involved in crash. In terms of economic costs, consider the direct cost, okay. It's 242. This is according to the NHTSA report. And Now, the intangible costs, indirect costs, considering everything, that you can see that a lot of costs reached $836 billion. So, and thanks to the autonomous technologies, recent years, we have seen a lot of research development and design and even market promotion of the applications of at different levels of sophistication. So we hold a high hope. But in the meantime, we understand that there are some fundamental problems that we need to work, to deal with. And again, I mentioned, current literature has very little really effort, focus on the differences among the vehicles in the fleet. And that's where we think it is necessary. We want to get into this subject because it's practical, If you want to really move from the lab to a real world implementation stage, then you have to worry about this. Simply the vehicle spacing, different vehicles, different sizes, different, braking systems, different abilities. How do you handle that? All right, so the objective we can see that is we want to investigate the impact of other factors, including the vehicle roadway surface, and also other factors on the formation of the connected and automated vehicle fleet. All right, so issue 1, as I mentioned, on the roadway resistance. We know that poor pavement affects the friction, it tends to cause accidents. Federal highway estimated at 70%, about 70%, and crashes in the wet pavement, situations, maybe because of the friction problem, So improvement needed. Well, how to address this problem? I mean, all the years, many states, many labs did a lot of work on the testing. I'm from Ohio. Ohio DOT every year spends so much money, sponsoring so many projects on the pavement material testing and everything. But to field work is expensive, timely, time-consuming too. So another approach is to do lab plus field sampling, and then do some computer modeling, try to understand, spending less time, and then less money to find out how we can improve the roadway friction. This is the simple way in the lab. We do a lot of lab work like this. The problem is, there are short and simple tests, always with assumptions, because this is in lab environment. We do some sampling. Roadway, these are all real pictures from our lab. And you can see that we do measurements, but those are short-term and isolated locations or limited number of locations. You can't do like the whole system-wide. Imagine in the U.S., we have a huge, roadway system, and it's really hard to keep track. Now, in reality, the friction is affected by the two things here, On one hand, we have the vehicle wheels, tires, keep polishing the pavement, so make it more smooth. Therefore, that will reduce the friction. But on the other, because of the bad weather, rain and snow and freeze and thaw, whole process is going to expose the aggregates. So we'll make the roadway more rough, Those will help increase the friction. So you can see it's not a very straightforward problem. I mean, the friction, you can do tests, you can do all different things. But how do you handle that? Well, we all have the background that we always use a stopping sight distance to estimate if a vehicle can be safely stopped. Stopping sight distance has two components. One is the reaction. I'm going to use the pointer if you can see it. It's hard to see, but anyway, the first term is reaction term. And that is vehicles traveled during the time of a reaction. And the second term is the braking distance. Okay. In the context of autonomous vehicles, of course, the first term we don't worry about much. Okay, and we focus on the braking distance part. Now, AASHTO published their green book, and all those years updating, and you can see that for different pointer, again, it's not quite working, but if you look at the left columns, at a different speed, the frictions for vehicles, that's on the most right two columns, you can see that the friction coefficient is changing. So we know that we're engineering, we know that it's not like high school physics. The friction is defined as a constant. As the speed increases, the friction coefficient decreases. We know that. And now, in order, imagine there's a huge, enormous burden really on a AASHTO or whoever maintain the database for the whole state DOTs to maintain a database of the friction, different parts, different sections, because it could be built differently, different material use, the different use, in other words, different ADT, average daily traffic, right? Different vehicle load, that can make a difference. So that how do you keep track of the changes in the friction? So instead, in this NCHRP report 400, it was suggested that we use this formula. In other words, friction coefficient can be calculated. Okay, in here, then we use a 3.4 meters per second square to represent the formula at the pointer. Okay, A here, that's the deceleration rate. All right, but it's fine. Many people, comfortable, but in reality, data show that the 90% of drivers, okay, in fact, they are taking greater than 3.4 meters second square at deceleration rate. So this is all due to technology advancements. Newer models, the braking systems can work better. So we not need that long distance to cover. However, in order for the whole generation, okay, of the vehicles or spectrum of different populations, different vehicle models and everything, to operate safely, so federal highway, use a very conservative, you can see that some numbers, okay, not to define the ranges. Okay, you can see this is at the 100 mile per hour, and this is at the 60 mile per hour. You can see that the last column on the right, you can see, okay, that stop sign distance is a huge number compared with the braking distance. Now, consumer reports, okay, data we found for most of the cars going from the left to the right, you can see, is my mouse working? Do you see that? Doesn't show this either. Okay, anyway, from left to right, you can see there are roughly 35 meters for the braking distance. But then you look at on the right three columns, those are larger size, okay, vehicles. You require a little more, like a 45 to 50 meters braking distance required. But if you compare those numbers with the federal highway, you can take a look at the red bar on the right. The stopping sight distance is huge, okay, for safety reasons. But is it efficient? We don't know. We'll see. Well, if we reduce the speed to 50, if you look at the top on the top of the chart on the right, 50 kilometers, that's a very low speed, right? In terms of the braking distance, you can see that the other vehicles, vehicle type 1, 2, 3, they're taking much shorter distance to brake. But the one on the right is from AASHTO, okay? They're to be safe, so they would require a much longer, okay, braking distance. Even in case of a poor tire. We know that, worn tire, ability to stop is not good, and still is much smaller than the Ashton's number. So what do we learn from this? We learn that different vehicles, different tire conditions make difference, not simply just pavement friction. Now, again, this is what I mentioned. It's not a friction coefficient. It's not a constant. It's not just simply by force divided by the weight. In terms of the concrete and the tire interactions, we have to consider other two things, adhesion and also hysteresis. Now, the first one, adhesion, is at a micro level. We can see that in the contact. But the other one, hysteresis, they're more at the macro level. So those two sometimes work against each other. So even if, you're measuring, you're doing experiment, you're only covering part of the story. What if, one part of in the same county, even in the same roads, what if one part is getting more rain or getting more heavier, or more large size of vehicles just passing that part of the road? Friction coefficient could be different. It's changing. So to summarize, all right, three things we already discussed. Roadway surface, yes, they vary from location to location and time to time. And tire tread, tire conditions, that can be a factor too. From our, we have a lot of data on this. We found that tire condition and also the pressure, inflation pressure, can make a huge difference too. And the braking system, larger size vehicles tend to be heavier, smaller size, lighter, but braking system, some are more effective. The same thing, just you do it comfortable braking, not like emergency, that kind of not in the uncomfortable situations. You will see that the braking distance is different. All right, so that will bring up the second issue there. How do we model it? Given we have all those different conditions affecting the ability for vehicles to stop. You can see that. We mentioned from pavement to the braking system of the vehicles, to the weight of the vehicle, to the speed it's going, to the tire conditions and everything. We understand, with the connected and automated vehicles, a vehicle can communicate with the roadside units. So if you drive, people assume when you drive the different parts of the roads and through the communication system, you will learn what is the friction coefficient. Well, the question is how accurate is that number of friction coefficient? How frequently is that number updated? Right? The friction coefficient, do you not update it? And also, how do you handle the variations and different vehicles with the different capabilities to stop, tire conditions and everything? So really, it's a very complicated factor that we need to consider, not simply just the friction coefficient. I'm not saying we should not sponsor all those research projects on friction coefficient. That's a fundamental we have to, and that's a main part, But if you're discussing autonomous vehicles, the fleet operation, we would have to consider other factors. So here, we know roadway resistance. It has to be overcome by the driving power, driving force, and then gradually from this, flow chart, it can go to, because we know the power, it has to do with the engine load and everything. So the last one shows, total resistance, is related to the engine load, the weight, and the speed. So now we understand, this is a basic physics. You have to have all your driving force to overcome all the resistance forces. And once at a given power, then the speed, how fast you're going, and also the driving force, the product of those two is a constant. So in other words, if you go faster, you will not have as much driving force. That's why we start from gear 1. We don't start from gear 5 because your driving force, in order to gain acceleration, you need a lot of driving force. We have to slow down. All right. So we know the internal combustion engine is not very efficient, roughly 30-35%. The others are all wasted, you can see. From the chart on the right side, you can see, all this used is mainly to overcome, rolling resistance and also the dynamic, aerodynamics. And of course, the braking, there's a high percentage. Why? Because it handles the slowdown of the speed. And then you need to accelerate, right? And that's you have to use additional, gas to do that. And also in the meantime, we need to realize the braking, process is not like immediate. It takes a little time, okay, for the system to react to it. Different vehicles, again, this chart could be different. The timing in between, that little t there, could be different. And if you look at the right side here, okay, the aerodynamics and the rolling resistance plus the grade. Grade is a huge thing. Not all, compose the vehicle loads that need to be overcome. Okay. Now here's a chart that shows everything you can obtain from a vehicle, and this is what we obtained. Okay, just show one example. The RPM, how fast the engine is, running, and we know the fuel rate. Okay, how much fuel is supplied, and we know how fast the vehicle is going from onboard GPS, and then we know the engine load, how much effort engine is working on, spent to work on this. Now, all those things that you can measure, and hopefully, some kind of like index, composite number will be generated, that will address all those different inputs, as you can see, vehicle weight, speed, and pavement condition, tire pressure, engine RPM, and then everything there, so that by using this, what we call the dynamic load index, we can relate it to the ability of the vehicle to stop. Again, not only the friction coefficient, but also the vehicle condition, the braking system, everything. So by using that, then we hope to build our base model. All right. Now, this slide shows that the ability to collect that data, is there because the EPA required, after 1996, that you have this, OBD2 that will provide. You should be able to capture that information. So on the engine, the driving train, and all the powertrain data, and all the other, related information in operation. So come back to this basic picture and also the mathematical relationships. We can see that the first equation here is to, this Newton's second law, to overcome all these different resistance forces. And the second equation, in fact, addresses the engine power, And the engine power, the input, the U, The last term, U, is the engine's input, how much gas you want to give, Roughly consider that as a fuel rate. And you can see by looking at the sequence, we have to have the formation of the platoon formation. You can see that one is following another. And if you pay attention to I and I-1, the leader is, leader, and we starting from I-1 and I+1 and so on. And you can see the E, the L is the minimum distance between them. E is in the error in adjustment there, And you can assume the same speed to develop the basic model, but in reality, you need to change the speed. And again, error is the minimum distance or spacing between vehicles. Now we come to a more, mathematical, more control theory side. So I'm not going to get into too much detail in this. From that, two equations. So we start to build the block diagram. If you're in, mechanical engineering or electrical engineering, you may be able to read this. You can see that on the right-hand side is the leader, and then the I-1 vehicles are following the leader, and the vehicle I is following I-1. The relationship, you can see that here. Basically, we says it shows the relationship between the vehicle I and the vehicle I-1. You can see at different levels. You have the engine input. I really need to have the pointer work. on the leftmost, okay, that's like x, the derivative, the third derivative, that is the engine, input there. And then they come to the second derivative, and that is the acceleration and and also the speed as the first order of x, and then the spacing. So you can see that all those things are related to each other. Now, one thing in particular is the error term here. So we want to model the errors, because that's where the dynamics. We do not want the errors to be too big, okay? Because that could, if you separate the vehicles, it's fine. But if the vehicles are getting too close, that's a safety, concern. So let me just briefly explain this. Okay, we introduce a delta. Okay, if you look at the last term, it says is the delta xi is the spacing between the two vehicles, consecutive two vehicles, minus L is the minimum spacing that can require absolutely for safety. And then we add another term to be the vehicle of speed of the vehicle, which is vi, minus a capital V. That capital V is, okay, sort of like the system-wide speed. You can consider that as, a speed limit. Okay, for example, in the local roads, okay, the capital V is smaller, but if the whole fleet is going on a highway, that V is larger. So it's because of the difference between that V, okay, your current vehicle, and also the capital V, that will, cause you to start to adjust things, to make some adjustments. All right. So you can see, okay, this is the distance. If you took the speed, and this is acceleration, okay, there is a relationship exists there. I mean, we do that because it relates to the stability. Okay, what is the stability concept, folks? Okay, on the left side, you can see that the first vehicle start to make some changes. I can see my mouse cursor moving, but you cannot. It's pointer not working there. So anyway, but if you see that the second vehicle also, right, the first vehicle makes some changes, and the second vehicle will make some adjustment. You can see, but then after a while, everything stabilizes, right? You can see that, and you'll remain calm. In other words, this disturbance, it's like gone. But if you look at the one on the right, you can see that, right? I mean, it starts to fluctuate. You have like undershoot, overshoot, undershoot. Okay, in this case, that possibly can lead to, unstable situations. All right. In other words, you think about a fleet. A fleet is going there, and then they're going fine, following each other. Some with a larger space and some with smaller space. Again, from the definition there. But then suddenly, if the leader start to make some changes, okay, and then you will see the whole thing is falling apart. That's unstable. That's not good. We want to be just a little bit, adjustment, automatically just not by driver, and then the whole fleet will become still a fleet, remain as a fleet, and it's keep going. All right, so, so mathematically we have to, do some calculations to find the stability. Okay. Now, one simple rule to do that is the errors from the spacing between the front vehicles and the errors between your vehicle and the vehicle in front of you, okay, it should be decreasing, right? I mean, the ratio should be less than 1. So only that condition is satisfied, we can guarantee, can we guarantee that the disturbance will die down, right? So in other words, we want to make sure that the value or the norm of this ratio Ri, that's between any two vehicles, will be less than 1. So in other words, there's a dampening effect, so that it will reach 0 finally. Okay, then it will maintain that. And to do that, of course, do some calculations. So this is in the Laplace, domain, and then we found, in order to make this R of I, that's the equation showing the red text there. We want to make that sure that the value or norm that is less than 1. It's difficult to do that in this fashion, but we have to use a frequency domain. Again, this is electrical resonant control, so we do not have to stress so much. So the equation we found, okay, in the frequency domain is this term. To make this term at least, or we call it less than 0, then we can maintain the stability. Now, if you look at every term, Okay, all those parameters is positive. The frequency W, or you want to say omega, I think this is looks like omega. Okay, you can see that the first term is with this order of 6 in the power, and the last one is 2. So all the others are positive numbers, so it should be fine as long as the midterm, this term, if you want to make this, not less than 0, then the whole thing is guaranteed to be stable. So based on this, we start to change, to do some testing, and to avoid, this is again in the context of a control, the system pause, because pause that's tend to make the system, unstable. So one must stay away from those pause, not to make the system unstable, by carefully selecting all the parameters in the model. So what we're looking at, what parameters will be good, what parameters are not so good. Okay, so we have to give some, propose some criteria that you can see here, and we have the rise time. Okay, rise time, again, if you can see that, is, the whole thing, jumping to the 90% in there. So rise time and then settling time, you can see that. Okay, how fast it will settle from this chart. And that's the thing, those are the things that we're looking at. But specifically, we're paying attention to the undershoot. Okay, the overshoot is okay. That's tend to separate the vehicles, safe. But the undershoot, means the vehicles getting too close. That can be dangerous. Okay. This is our base model. You can see that we assume the 10 vehicles in the base model. And basically what we see is, again, from right to left, you can see the first vehicle will pass the vehicle speed and also the location information to the second vehicle, because it's connected vehicles, right? Autonomous vehicles and connected vehicles. So we share that information. So each vehicle, after receiving that information, will work as a unit. This is the ICE vehicle. This is the ICE vehicle, the flow chart. Getting information from the lower right-hand side part, and then all those different model parameters will function that will keep the vehicles going and following the leader. And now this one, again, this is the error term we discussed, and it makes a contribution to that. And this will be the leading vehicle, the leader. The leader will go, the one chart and the lower part of this slide. It shows the leader. This is just we assume the leader make this kind of changes, but in reality, a leader is making, it's like giving the order, right, to the whole fleet. And sometimes if you're coming to an intersection, for example, leader will have to stop, or going to a more congested area, and the leader will slow down. So all those, changes here, and we assume the leader will experience this. So leader is not following anything. Okay, it's like making an adjustment. And then all the other vehicles in the fleet will have to follow. Okay. Let's see here. Now, this is a simulation. Okay, we run from the base model, and you can see that when leader has these different changes in the speed, and all those vehicles, okay, the lower one shows the spacing. The first line, which is yellow, if you look, it's kind of hard to see. The yellow line, you have some undershoot and overshoot, and that each line shows the spacing. It's the spacing, okay, not the trajectory, but it's spacing of the pair. For example, the yellow line shows the spacing between the first vehicle and the second vehicle, and then the next line is kind of like from my here, it looks like a blue, okay, a light blue. That line shows the spacing between the second vehicle and the third vehicle. So you can see that, you do have some undershoots and then the overshoots, and then gradually you can see that the whole thing is, stabilizing. Okay, so this is fine. But if you look at this undershoot, the yellow line will reach to a number, I don't know whether you can see, it's like a 0.3, a little bit over 0.3, that's a meter. Now we understand that, well, that's what, 30 centimeters. That's dangerous, too dangerous. Okay, so that we have to make some adjustment to the parameters. Okay, because the undershoot, overshoot is okay. The larger, we're not so worried about it. Okay, but the undershoot is where we want to make sure that we want to avoid. Also, if you pay attention to the settling time, you can see that it's still fluctuating until after 100 seconds. And that's not good, right? I mean, it's like almost 2 minutes if there's any disturbance there. If the first vehicle makes some adjustment or the leader vehicle makes some adjustment, other vehicles are taking so long, that's not very good, okay? So in other words, selecting of these parameters is going to make a big difference. So how do we do that so that we can guarantee a fast, a better, convergence process? Now this one shows those some testing we did there. So what we're looking at is, if you look at the one on the right, start from 0, starting to reach 1. 1 means the total stabilizing. Okay, that's ability to stabilize. Okay, but the lines or the formula shows on the left, it shows different things. If you look at it, we have the rise time. That's one indicator, for us to select the parameters. Again, this is the control equation. We want to make sure that we want to avoid those poles. Okay, this mathematics sort of like divided by 0. It's going to explode for sure. We want to make sure that our parameters we select will stay away from those poles. Okay, the poles on the left, fine, but it's on the right. That's a problem is if you know the control theory. So we're looking at the rise time. We're looking at all this settling time and so on. So then the 3 things listed in the text there. Okay, we want to make and test with the different parameter combinations. Okay, and we want to make this a string stability. In other words, we want to make the system stable for sure, and also we want to select the best ones. Okay, by looking at these times. So we did a lot of combinations, and we're actually improving the way is mathematically to say that how we will be able to reduce the time to find the right parameters. Well, the reality is, as the vehicle is moving, the whole fleet is going on. Input from environmental conditions, from the vehicle conditions, from the pavement conditions can change. In other words, we have to constantly regenerate this. In other words, we have to do this fast, okay, so that the parameters will be changed, on a time base, real time, if we can do that, okay, fashion, so that any condition can be addressed immediately. Okay, you read input from a vehicle, okay, read from roadside, and you constantly make an adjustment to those parameters. Okay, and that's why we want to make sure that the those indicators, those time indicators are satisfied. So that is a base model. Now, when we have the base model calibrated, or still, by the way, I forgot to mention, this is a project sponsored by CCAT, and it's ongoing, and we've done, the work we so far, presented, and work is still going, and that's going well. But here we come to the introduction of the disturbance, right? I mean, we follow leaders fine, but we have to consider the realistic situation. Okay, in other words, sometimes not leader, but one of the vehicles in the fleet will have some problems. For example, one vehicle hit a black spot, black ice, okay, there, and then they start to have problems. And then what do we do? The whole fleet, will they still be able to keep the formation, okay, maintain the fleet? That's where we started to introduce disturbances to the fleet. You can see that. As shown, you can see that between the second vehicle and the third vehicle, we intentionally introduced something to that. You can see, okay? And this is just to show some interface that we did there. And this enlarged, you can see that this is where we introduced that. And you can see there's just one experiment, simple experiment, and that's between the second and the third vehicle. So what you look at here is you look at this, not the yellow line. The yellow line is still the first, but the blue line, okay? You can see the blue line change is not even noticeable. So in other words, there's minor adjustments vehicles can handle. The system is able to just handle without any problem. You can see that, right? You can see it's like the first vehicle, the leader vehicle makes some, speed changes, but then between the second and third vehicle, there's some disturbances, and the system is able to absorb that without any problem. All right. So Now, we also did an experiment by, change and make another, change. This is introduced between the first vehicle and the second vehicle. Okay, the leader is, the front is still making changes because in the front, the leader does not care about the vehicles, following, but it's like only worry about what's in front because to be safe, right? So all these vehicles behind the leader are supposed to change its speed and acceleration. So, and to follow that, right? But now we introduce something between the first and the second, and then this is you can see this is a much larger magnitude, and again you can see that little signal that disturbance introduced. And if you want to look at the results, look at the yellow line. And that is yellow line is the spacing between the first vehicle and the second vehicle. That's where we introduce disturbance, between them. You can see that the huge, right, it's like overshoot so much. Again, we're worrying more about the undershoot. The overshoot spacing increase a little more is not really a critical safety concern. But still, this is large. So in other words, the parameters we're using may not be, appropriate, or we may be improved. Okay, we may be able to improve the parameter so that we do not say, so much, overshoots. So you can see that different disturbances introduced to the system can result in the fleet to change, the formation to change. Okay, so we have done, this work, and we're, again, this is ongoing. So in the next, what we'll do is we want to, characterize the impact, and also want to define. Now, those two words mean different things. Okay, characterize is we have, as I mentioned before, different kind of input, different factors that are affecting, vehicle operation. Okay, we mentioned that you can have the roadway friction problem. You can have the vehicle braking system. You can have the, large size, small size. You can have the tire condition, different factors. How do we characterize that? How do we make that, convert that into different types of disturbance? Remember, this kind of disturbance has very little effect. You can see that, right? So we want to sort of like do the mapping, so we can characterize different disturbance from the conditions. Okay, so that we can use it different situations and then to be introduced to the system. Define, by using the word define, we mean to find the magnitude. Okay, so that's the work we continue. We'll try to define the different type of disturbance. What's the magnitude? So that when we introduce in a table here, again, I cannot show, but you have some numbers in there to show what's the magnitude. Same here. Okay, so those are the things that we will continue to work on. And so, the whole purpose is to establish proper parameters, okay, define a range so that, the whole fleet will run safe. And in the meantime, if we can make this fleet run more efficiently as well, that'd be great, okay? So that will conclude my presentation. Any questions? Yes.
So our data is commodity cost. So thank you. So yeah, of course. So a great presentation. I'm Ashu, like the Sandy Maker News Needs. I'm a tech lab at MCD student here at the University of Michigan.
Yeah.
I guess just wondering about like what's so for different like fleets, I think you were talking about like average braking distances of commercial vehicles, like for example sedans and pickup trucks. But like, do you also address fleets of, for example, like a connected fleet of like freight trucks, so like 18-wheelers? And if so, what are the unique challenges that come with those kinds of vehicles versus like a fleet of just normal cars?
It's a good question. Yeah, the research method applies to everything. Okay, we can address like a commercial trucks fleet, but every vehicle will have a different characteristic because they are heavier, their ability to brake, right? From a practice, used to be, now I think it's better, but I still see that in Ohio. You see a long stretch of a roadway, with the tire skid mark. I mean, it's harder for the trucks to stop. So remember, the friction coefficient to them work differently, okay? So, and their tire also, all those things, the methodology we believe it should apply. It's just like, I hope we can, continue work on this, after its current project. And then we can, move into the implementation stage. Yeah, it's good. Any other question? Yes.
Hi, Professor Yi. That was an excellent presentation. My apologies. I came in the middle. I was in another session. My name is Krishna Kumar Nedanuri, a professor of environmental engineering. It's from Central State University. As I go through the presentation, it's a very complex problem. We could clearly see the control systems getting, very crazy under some conditions. So I have two questions. Give us your insights on, how the algorithm adapts itself, across the seasons in a year. You have a winter, you have a summer. That's one question. The second question is, again, your insights on extreme weather conditions, how your algorithm would respond. Thank you so much.
Yeah, thank you. Yeah, it's good, good questions. This is to say, when you really consider extreme, weather and the climate, seasonal, changes, the factors, how do you do that? Yes, remember the one of the slides we show that all these different factors. In fact, we hope this is a real important thing that we're working on it. We may have some breakthrough finding. I'm just optimistic and say that. Where is that? Yeah, this one, I think. Yeah, we hope to use the dynamic load index, okay? Because in here, everything in the wintertime, your tire pressure is different, and the pavement coefficient is different, but we were preliminary results, because we're not making a conclusion yet, so I didn't share. We made some good, look at this. Use the combination of these and also with others like pavement factors. We're running some doing some study. We try to develop that dynamic load index. Okay, so to use that to relate it to all the condition changes that address the weather condition, different seasons, and size of vehicles, and so on. So, but this one again, because it's not concluded yet, we have not, do detailed explanation on that. It's just the concept there. The good question. Yes.
Hello. This is Brian from UMTRI, University of Michigan, and I'm assistant research scientist in UMTRI. So it's a very interesting presentation, and I'm very, very impressive. About the results you see, like the very short gap, like the 30 centimeter you just mentioned. So it's kind of a very dangerous situation, when we try to follow the vehicle and in the fleets. And so in the end, you try to, I know it hasn't been done yet about how to implement that into the connected vehicle environment. So my question is, how do you have expect anything, if you try to implement those into the connected vehicle environment, are we going to see any maybe faster response from the following vehicle, or maybe we will even see the even shorter gap, since the driver, can expect what's going to happen in the first lead vehicle. So, the driver at the very end of the fleet, they may also, are we going to expect their behavior will be adapted or changed?
Yeah, very good. There are two, I guess you mentioned two issues. And the number one is how safe is it safe? It's a question, all right. 3.3 meters or 30 centimeters, is that safe between vehicles and getting so close? I'm an engineer. Okay, I've been teaching. I work in the old Minnesota DOT years, project manager, and I relate. I guess I like to put it this way. Okay, I like to relate to practice. Okay. Even though I'm doing a lot of theoretical work. To me, 0.3 meters. I mean, you mentioned about how close you can get closer to get more efficient. I don't feel safe, honestly, because we're still looking at the tire pavement interaction. Okay, there's got to some errors, right? The material may not be, consistent. I mean, in terms of the certain properties. So part of the roadway, others are fine, but a part of the roadway, or maybe because of the way it is constructed, or maybe because other factors are affecting that. I want to leave some safe space there. So for error, okay? So, but I am not able to answer that, how safe it's safe, but for the methodology, we're developing wise, you can define, when we define the parameters, like model parameters of the base model, we can define, 0.5 meter is unacceptable, or even 0.8 meter is as a minimum. Then we can define those set of parameters to be implemented in there. Okay, so that's number one. Number two is, to really to test that. I hope we will continue, work on this, with Michigan, with, good researchers on safety and to actually do some testing. Okay, if we come with we don't need so many, we just need 3 vehicles. Okay, 2 vehicles, you don't know because a leader is a leader and you only 1 vehicle, but 3 vehicles will be enough to test on that. We have this MCD, we have the test track, and hopefully, we can, and of course, this will have to work with the auto companies to do that. But I look forward after we finish and everything we feel comfortable, and I will promote for a continue to work on this. Good. Does that answer your question?
Yeah. So that I think the back to this already like this how bags will react to such before gas and out of the.
I'm sorry, I may have missed that you mentioned about the human driver part. Yeah, this is assumed to be a autonomous vehicle fleet, but in reality, we have the fleet and the human driver mixed. The common vehicles or human driver operated vehicles mixed in a traffic flow. Okay, but its advantages. You have some reports, researchers done through simulation. It is advantages in the case of a mixed traffic to have autonomous vehicles move in the fleet. So that's why, because people know that this is a fleet and there are no driver situations. So it's easier to operate and more efficient to operate. For example, going through certain intersections, we know how long it is, and these guys are just without any human factor influence will go through intersection or exit. So it's the efficiency and the safety. Okay. So there's advantages to do a fleet, but then in the fleet, that's our research topic addressing. How do you really take care of the differences among the vehicles to be safe? So, yeah, good. Yep.
Oh, hi, Professor. This is Yun Chang from Purdue University. I'm thinking about some corner cases for your system. The first corner case, the system may experience is, what if the connection between the first vehicle and the third vehicle, the information connection break? And the second corner case, I'm thinking, what if there's a pedestrian in the road? The lead vehicle will have a abrupt stop. So what will happen? I'm just curious.
Well, you ask me, I cannot answer. Good question. Okay. Now, we rely on communication. Okay. Now, in this case, we made it, the reliance on communication, minimum. In other words, the second vehicle only receive information from the first vehicle, in other words, from the leader. And the third vehicle only receive information from the second one. Okay. So we made it the minimum level, but they said if the communication is broken, then I think that there should be some safety thing. So probably the fleet is going to dissolve, will not have a fleet anymore if there's no communication, but still a safety distance, okay, okay, and the spacing should be maintained. And like we try to introduce the disturbance, right? I mean, you mentioned about what about a deer or even a squirrel, running through across the street? That can cause some problems. The system is able to detect, but in case of pedestrian, is a huge. And I hope the system, is able to recognize this is a squirrel and that is a human, and so that will react differently. Good question, but we have not, considered that in depth. We're just developing the methods. Good.
Thank you. Sure. Hi, I'm again Manekta from the University of Illinois. Thank you very much for the presentation. I am not in this field, so I think this will be a higher level question on this slide that you're showing. So I do get that for a stable system, you want them to be in a specific range. But since we are talking in the terms of the connected and autonomous vehicles, why isn't the solution is the Ford follows the same path with one? Like there's no time lag. Like why is there a time lag in here? Like why don't they all slow down at the same time? Like just for something, because I don't know.
Very good question. I mean, you can have an assumption that all the vehicles in a fleet work like one single vehicle. To go at the same time to stop, it's like a rigid body. Although you have a few vehicles in there, so that's what your question is, right? Why can't you just like a whole thing, assuming all moving together? It's some research, publications, especially in concerning the operations, and they do make that kind of assumption. But our assumption is to make it more realistic. But there has to be some time lag. Okay, you can communicate, but due to the differences between vehicles. So again, we're addressing the differences. Okay, the vehicles, for example, accelerate for the acceleration part. Smaller engine vehicles, when they accelerate slower than the more powerful, larger size vehicles with more powerful engine. There are some differences. If you have all the vehicles, again, all the same brand, same year, same kind of tires, you cannot make that assumption. They're all moving. Even though you're in between of 10 vehicles or 6 vehicles, they can move as a rigid body, stop, go, okay. But in reality, it's very difficult to achieve that. But it's a good question.
Thank Dr. PingYi, and thank everybody, and invite you back to the main ballroom for lunch.
Thank you.